And we wanted to welcome Dr. Jonathan Woodruff from University of Cambridge, who's working with eliminating the test gap between specification and implementation.
Good afternoon, everyone. So this is a bit of experience we've had with the development of a new instruction set architecture extension where we've been able to avoid building a test suite for our extension, which is pretty complicated, and instead are using purely model equivalence verification. And we've heard many related experiences this week. And so it's similar to some things people have said, but we're hoping this can be something that's easy to use and an open system so we can build a little community around verifying RISC-V processors together. Okay, so let's talk first about unit tests for architectural compliance. So my impression is often the flow is for developing a processor. You start with a unit test suite, and the unit test suite is helping you with architectural compliance. You want to make sure that you at least roughly do what the architecture says, and for that you have a long list of tests. Each one is supposed to test one small feature. As we saw in a couple presentations ago, generally you have a whole bunch of boilerplate around that, so very often you're failing 60 tests when there's actually just one problem. So it's not ideal, but this is what we've typically done because it's perceived as kind of the simplest thing to start with. An alternative, which is widely used also, is model equivalence verification. I'm kind of inventing these terms, but there's a family of things where instead of having a unit test suite that tells you what behaviors you should build, which has been hand composed by someone, you simply have a model, and that model behaves the way you wish your implementation did, and instead of unit test failures, you just have divergence from the model. And so this is a different way to develop. Instead of running a bunch of individual tests, you're just reported where you behave differently from the model. And there's at least two ways to do this. One is directed random test sequence generation, where you generate random sequences and just make sure for some definition you do the same thing that the model does, and you're told when it doesn't work. Another common approach is formal model checking, where you have a model, possibly in Verilog, and your implementation also in Verilog, and then you run formal analysis tools that in some way tell you that your model and your implementation do the same thing. So why is it that model equivalence isn't the norm? Why don't we just use that from the beginning? Why do we even have unit test suites? And at least it's because they're perceived as too hard to start with. It's easy to just kind of hack up a few tests and assemble them and try to run them. But what if using this way of development and verification was easier to use, both easier to compose and easier to use for the designer when they're bringing up a brand new design than a unit test suite? Then you could avoid having to construct a test suite, which actually is imperfect in a lot of ways. I may not have mentioned in the previous one, I should have. Unit tests also have, not only are they difficult to compose, but there are very large pieces of the design that aren't covered, like the forwarding paths in the processor, generally the memory consistency. And for these things, you generally break out your model-based testing. But it's possible to cover all. If we had easier to use model equivalence testing, it would be possible to cover all of those with the same tool without having to maintain a separate test suite. Okay, so our approach requires instrumentation of the pipeline. And it builds on Clifford Wolf's RVFI interface, which is the RISC-V formal interface, where the pipeline reports a rich trace that tells you all of the state updates due to that instruction. But we add another piece, DII, direct instruction injection, where we can have a test generator produce instruction sequences and feed them directly into the pipeline. And this allows us to do very simple instruction generation because we don't have to worry about actually producing correct programs in memory where you have branches that branch to the right place and all. We're just consuming instructions from a FIFO at the beginning of the pipeline. And this allows us to very simply create the equivalent of unit tests for architectural specification. So on the right is, just as an example, this is our simplest verification engine using quick check. This is our generator for all the arithmetic instructions in I. All you have to do is list the instructions, and if you come up with a new instruction, you add it to the list, and it begins being generated in combination with all of the others. And you're able to see not only does it behave the same as the model in some cases, but for a very large number of values and in combination with all the other instructions on the list. So you don't have to maintain a separate unit test suite. You simply add to the list, and you're verifying in combination with the rest of the things. Also, there's two other benefits of doing this. By injecting directly into the pipeline, we get deterministic pipeline timing for injection, so we can reproduce things like forwarding bugs, even as we shorten the counterexample. That leads to the last one. We get automated counterexample reduction. So if you have to produce valid programs that run in memory, it's quite difficult, or at least more difficult, to automatically figure out what instructions were unnecessary to the counterexample. But by feeding sequences of instructions directly into the pipeline, we can automatically eliminate instructions, keeping the same timing relationship between them to get down to the absolute minimal counterexample necessary to reproduce, which is really handy if you have a pipeline with lots and lots of prints. It's possible to have 2 or 3 instructions that actually produce the problem instead of having to run through a whole unit test. Okay, so this is the TestRIG framework. This is what we're hoping people can contribute to and join in. So it's composed of, each setup is composed of 3 interchangeable components that communicate over TCP sockets. So the RVFI interface is a binary interface that Clifford came up with. So we've adapted it to a byte stream interface for talking over TCP sockets on a host. And then the direct instruction injection interface also is a byte stream interface so that we can easily instantiate Verilog simulations or Haskell simulations or whatever language your model is running in, or your implementation is running in, or your verification engine is running in. They can communicate in an agnostic way across sockets. So the first interchangeable part is a verification engine, and this generates the traces and receives back generates the instruction sequences and receives back the instruction traces, the state update traces, and ensures that the two are equivalent. And if it finds that they're not equivalent, it then has the opportunity to try to generate simpler traces or smaller traces that also show a divergence. Then the last two are a model and an implementation. Now, ideally for a model, you want something that's both a specification and a model, so it's easy to read, easy to maintain, but also executable, because we're going to be feeding instructions into it and seeing what they do. And then, of course, your implementation. And because these talk RVFI Rivety, we call it, because the models and implementations speak Rivety, you can mix and match between models and implementations and do tournaments between various implementations. So we're hoping we get more and more implementations, more and more models supporting the Rivety interface so that we can easily plug in and compare one another's implementations against each other. And as people have more interesting verification engines also. So these are our 2 verification engines we have at the moment. Our primary one we've been developing with is in Haskell and uses the quick check library, which is very convenient for doing exactly what we're doing here, generating random inputs according to the type that you specify. And of course, our type is just RISC-V instructions. Then we use a library so you can very easily define instruction formats. If you go look at it, it's actually very few lines of code because we have very convenient libraries for that. And we have 5 instruction mix generators, shallow ones, integer, memory, flow control. So for example, instead of a whole area of the test suite, you just have a generator that generates that class of instructions and tries to do a good job. And we have templates, just the beginning of templates for reaching deep states. So what you'd like is rather than just random individual instructions, you'd have sequences of instructions that could set up a TLB, a page table entry, for example. So our executable model we've primarily been using at the moment is based on SAIL. And the design goals of SAIL is that it's readable so that this can be not only your model, but also your specification. You'd like it to be your one specification such that if somebody changes their mind on how a certain instruction should be defined, and they go and change the specification, just as you might change a prose document, you'll immediately get counterexamples coming out of your verification before somebody goes and changes a unit test. The SAIL model is also executable, of course, and it has formal semantics, so you can prove things about it. So again, if we're just trying to demonstrate equivalence with the model, we've kind of lost the fact, we've lost the ability to how do we know that the model is correct? You know, nobody is writing down properties anymore. So what you really like is instead of unit tests of your implementation, you would have unit proofs of your model that can formally prove that your model has the properties you expect. And then all we need to do is demonstrate equivalence between the model and the implementation. Okay, so here's what we've needed to do with the main pipeline we're working with. So again, the direct instruction injection, it bypasses instruction memory. So for every PC, when I would normally go to memory to fetch an instruction, I instead consume the next instruction from FIFO. So it's just pulling a sequence of instructions. It injects it into the pipeline and pulls out the trace at the end. Now, inside of our little chassis, we need a replay buffer because instructions could throw exceptions. And as you can imagine, if you're generating random instructions, a lot of them are going to throw exceptions. And this causes the pipeline to flush, to drop some instructions. So every instruction that commits, every trace has a sequence number. And if it flushes, if it says that it's thrown an exception and it's going to flush, the replay buffer pulls out, instead of fetching the next instruction and losing some of the instructions that had previously injected, it replays the instructions it had previously injected. So you can imagine there's a little work in making sure that you have one trace entry out for every instruction in, regardless of what happens. Then the trade-off, of course, is that you're able to use much richer verification as you're bringing things up. So here's a really nice example of our counterexample reduction. So we injected a little fault in the spike simulators where whenever it added to instructions, the result always added to register values, it always cleared the lowest bit of the result. So we finally detected the divergence in a long sequence here, and a quick check after a few iterations was able to boil it down to the minimal number of instructions needed to reproduce the error. So this is producing an immediate with an odd value and then trying to add that. And instead of having the odd value in the result, it had an even value because it cleared the bottom bit. So this is a real thing. We've been using it quite a bit, and for very complex problems, we very often get the smallest possible counterexample we would need to work with. And this is very nice when you're replaying, looking at a trace of all your microarchitectural state. You can work with a small counterexample, which is much better than your typical test suite where you're trawling through tens of instructions at the very least to figure out where something went wrong. Okay, so our conclusion is maybe there's a case for replacing ISA level unit test suites with building a model specification and also instruction sequence generators, which hopefully are easier, and unit proofs of the model. And then finally, using this setup, there's a potential for much better verification that can not only ensure architectural correctness, but at the same time deal with all sorts of pipeline forwarding and cache hierarchy bugs also. So I don't know how much time, if I have any time left.
A minute.
What?
A minute.
A minute left. Okay.
So, perhaps any questions at this point? There in the back. I have to practice my throwing skills. Almost.
That's okay. So, congratulations for your job, because it's really good to have some formal verification gets improved in RISC-V. So I have been developing a RISC-V processor, and I used a RISC-V firmware from Clifford, and he has some things like the monitor that you can build and synthesize along with your core and put in a FPGA. So do you have something similar with your approach using D2 for this?
So we haven't used this in an FPGA yet. As you could tell, we were using TCP sockets, which are all running in simulation. But it's not hard for people who work with FPGAs, it's not too hard to have a TCP interface to a component on the FPGA. So we imagine in the end, you could be stimulating both across a socket to the FPGA and also on the computer. Now, if you're still waiting on software to generate the sequences and to compare the sequences, it's not likely to be any faster on the FPGA unless you had a sequence generator that was also synthesizable. So we have a tool called BlueCheck that also generates sequences. So it's possible you could have a model on FPGA and implementation on FPGA and communicate across sockets on the FPGA.
Okay, thanks.
Thank you, Jonathan. Next up is Nikolay Tusinci from OneSplit. Oh, sorry.
Thank you.